Hello everyone, and welcome to our session on space complexity analysis. Today, we'll explore how to measure and analyze the memory usage of algorithms critical for understanding resource requirements, especially in constrained environments. Let's dive into the details of space complexity. To begin, let's define space complexity. It's a measure of the amount of working storage an algorithm uses during execution. This analysis is important because it helps us estimate resource usage and is crucial when working in memory-constrained systems. We'll focus on key areas like memory allocation and the difference between auxiliary and intrinsic space usage. Space complexity explains the amount of memory an algorithm consumes as a function of its input size. This includes both the space needed for the input itself and the temporary workspace, or auxiliary memory, that the algorithm uses. When evaluating space complexity, we often consider both worst-case and average-case scenarios. Now, let's talk about how we measure memory usage. Key metrics include the space consumed by variables and data structures as well as the recursion stack space used during function calls. Factors that affect space complexity include the data types, the structures used, like arrays, linked lists, or trees, and the overall design of the algorithm. We typically express these measurements using BigONotation, such as O, 1, O, N, or O n squared. Space complexity can come in several forms. With constant space, denoted as O, 1, the memory usage remains fixed regardless of the input size. Linear space, or O, N, means that memory usage increases linearly with the input. In certain scenarios, especially with recursive calls, you might also encounter logarithmic or even exponential space complexities depending on the algorithm structure. Analyzing space complexity involves a systematic approach. Identify all the variables and data structures the algorithm uses. Evaluate how much memory is used in each part of the algorithm. Account for any recursion or iterative processes that add to memory usage. Finally, express your findings in BigONotation. This step-by-step method helps ensure that you accurately capture the memory requirements of your algorithm. In this slide, we have a visual demonstration of memory allocation in a sample algorithm. The animation illustrates how memory is allocated during execution, with animation showing function calls and the corresponding space used at each stage. This animation will help you better understand how memory is managed throughout the execution process. Let's look at an example focusing on recursive algorithms. In recursion, the depth of the recursive calls directly impacts the stack space used. We'll compare tail recursion versus non-tail recursion and discuss the memory overhead due to these function calls. A visual, step-by-step analysis will illustrate how recursive space consumption builds up and why it's an important factor to consider. To understand it better, let's jump into the Visual Studio Code and write a program and see in action. I am into Visual Studio Code. I'm going to implement a program that demonstrates different space complexities using several functions, and I'll explain the issues with non-tail recursion versus the tail call optimization technique. The program includes several functions. The first function, SumArray, calculates the sum of elements in a vector using a single accumulator variable. Since it doesn't allocate additional space that depends on the input size, its space complexity is constant, O, 1. Next, the createVector function creates a new vector of size n with all elements initialized to 0. Because it allocates memory proportional to n, its space complexity is O, n. Now, let's examine the issue with non-tail recursion. Consider a factorial function implemented using non-tail recursion. In this approach, after the recursive call is made, the function must multiply the result by the current value. This means that each recursive call has to retain its state on the call stack until the recursive call returns, resulting in O, n, space usage because the call stack grows linearly with n. To address this problem, we can optimize the recursion using tail call optimization. In tail recursion, we rewrite the function so that the recursive call is the very last operation performed, with no additional work to do after it returns. This is achieved by introducing an accumulator that carries the intermediate result forward. With this technique, the recursive call becomes the final action, allowing a compiler that supports tail call optimization, TCO, to reuse the same stack frame for each call. Consequently, this optimization can reduce the space complexity from O, n, to O, 1. In summary, the SumArray function uses constant extra space, O(1), the createVector function uses O(n) space due to memory allocation, the non-tail recursive factorial function uses O(n) stack space because each call waits for subsequent calls to complete, and the tail recursive factorial function, when optimized via TCO, can achieve constant space usage, O(1). Now let's run it and you will find the output produced is same for non-tail and tail recursion, but the difference is in space complexity. This example clearly illustrates how restructuring recursion using tail call optimization can significantly reduce the memory footprint of recursive algorithms. Let's go back to presentation. Managing space complexity effectively is key to building efficient systems. Some best practices include optimizing data structures by choosing the most memory-efficient option for the task. Limiting recursion by opting for iterative solutions when possible. Using profiling and testing tools to measure memory usage during execution. Continuously analyzing and refactoring your code as new constraints or requirements emerge. These strategies help ensure your algorithm remains efficient in terms of memory usage. To wrap up, we've covered the definitions and importance of space complexity, explored various analysis techniques, and looked at practical examples. The key takeaway is that effective memory management is critical to robust system performance. If you have any questions or further discussion on space complexity, you can drop in comment section. Thank you for your attention.